Hi guys, in this tutorial we're going to see how to use the star to delta transformation or the delta to star transformation. Now sometimes you can be given a circuit like that contains a setup like this one where you have three junctions. In this case we've labeled them A, B and C, and then we're trying to find an electrical equivalence of something like this or the effective resistance of a circuit like this. The method that we've used for parallel and series in this case will be tricky. We'll see some examples and then we'll see exactly how these methods will work. So in this case, of course, this is the delta and this is the star or the Y. So it looks like a Y, of course, upside down. Now, how do we use the delta to star transformation or the star to delta transformation? Well, for this tutorial, we're going to look at the delta to star. So we want to convert the delta and then convert it into a setup that looks like a star. And then we're going to work out a few examples. And after that, we're going to see how we would do it if we had a Y or a star that we wanted to convert to a delta. Now, let's say the resistors of our delta are labeled, say, we can put R1 here, and then we can put R2 here, and we have R3 here. Now, the labels, of course, are totally up to you. What I want you guys to get is the trick on how you can actually come up with these formulas regardless of the letters that you're using. And then for our Y, want to convert it into a Y. Let's label this this resistor as RA, and then let's label this resistor here. We can label this one. So we can label this one as RB, and then we can label this one as RC. Now, the trick to making the conversion, the first thing I would want you to do is redraw the delta with the star inside. So what I'm going to do is I'm going to quickly sketch the delta. So let's sketch that delta. So we have, I'll make it a little bit bigger. So I'll just create something like this. So in this case, we had A, B, C. So we have A on top. So we have A, B, C. And then, of course, we have our resistor here, here, and another resistor here. So here we have, this was R1, 2, 3. So we have R1, R2, and R3 down here. And then now we're going to put our Y inside. So you want your Y to stand on the same nodes A, B, C. So in this case, it's going to start from here. So we're going to start from here, come down, then go to this node, and then come to this node. So we have one resistor will be here, one resistor will be here, and another resistor will be this side. So we label this one as RA, this one as RB, and this one as RC. Now, how do we convert? So in this case, of course, the argument is that you are given what R1, R2, and R3, what they are, and then you're trying to find an equivalent circuit that will look like a star with the resistors RA, B, and C. So we're trying to first find what RA is, what RB is, and also what RC is. Once you can find these, then you can substitute this delta, the one in blue, by something similar or something equivalent that is going to be in form of a star. So how do we do that? Well, the key here is to notice this. If you want to find RA, notice that RA is between R1 and R2. So to find RA, we're going to multiply the two resistors it is in between. So we're going to multiply R1 and R2, then we'll divide by the sum of all the resistors that are making that delta. The sum, of course, which will be R1 plus R2 plus R3. So this is what is going to give us RA. And then in a similar way, to find RB, where is RB? RB is down here. And we see that RB is between R2 and R3. So multiply R2 and R3. Then again, we divide by the sum of all the resistors that are making that delta, which is the sum, of course, R1 plus R2 plus R3. In the same way, to to find RC, where is RC? RC is down here. It is between R1 and R3. So we'll multiply R1 and R3. So we'll have R1 times R3 divided by the sum of all the resistors making that delta, which is R1 plus R2 plus R3. So this is how we obtain RA, RB, and RC. So we can then replace at this point, we're going to have RA connecting at A. And then at this point, we're going to have RC connecting there. And at B, we're going to have RB connecting there. So in whatever circuit that we have, would replace the delta by the star. So we'd remove these now. We'd remove the delta so that we remain only with the star. So now let's look at an example to help you guys just see the application or how we actually use this to solve problems or circuits that might seem a little bit complicated. So let's see an example. In this example, we're being asked to find the total resistance for the circuit that is shown below. So let's look at the circuit. So to determine the total resistance here, first we identify what we're going to use here. Since we're looking at the delta to star transformation, we want to identify the delta here. And I want you to notice that the delta is going to be created in this side. So we have this coming this side, coming this side. Notice that in each side we have a resistor. And then we have three junctions, one there, one here, and one here. So this is going to be our delta. Now, how do we transform this into a star? So to transform this into a star, we want to create a Y inside this delta such that it stands on the same junction as the ones indicated. But first, let me just get that that delta. So we have something like this, then we have this, and then it comes down this side. So this is our delta. So we want to only have one resistor this side. So we see this is a continuous line. We have two resistors in that line. These two resistors are in series, so we can easily combine them. And the resistor in that line, when we combine them, those are going to be 41 ohms. So we have 41 ohms this side. And then when you look at the other side, this side, we have a 10 ohm resistor. So let's place that one here. So we have 10 ohms. And then this, in this line, we have 3 ohms. Now, what we want to do here is that we want to create a Y inside here. So by creating a Y, let's see what we're going to have. So our Y, we have these junctions. Let's indicate our junctions. So we can say this is terminal B. Then you can say this node, let's label it A. Then let's label this node as C. So our Y, one has to start from here. We have our resistor in this line. And then another has to go towards this node. And the other one towards C. So we can label the one going to B as RB, the one going to A as RA, the one going to C as RC. Now, how do we make the transformation? How do we find, let's find our RA, RB, and RC. So just like before, to find RA, we notice that RA is between 41 ohms and 3 ohms. So to find RA, we'll multiply 41 by 3, then we'll divide this by the sum of all the resistors making that delta. The sum, of course. So this is going to be 41 plus 10 plus 3. So of course, if we do the math here, RA will come out as 2.2778 ohms. So from there, we find RB. For RB, RB is this side. It is between the 41 and the 10 ohms. So we'll multiply those two. So you have 41 by 10. Then we'll divide by the sum of all the resistors making the delta. Again, it's the same thing, 41 plus 10 plus 3, which is just 54. So again, when you do the math here, we find RB as 7.5926 ohms. And then lastly, we find RC using the same method. So again, RC is down here. It is between the 10 and the 3 ohms. So because of that, we'll multiply the 10 and the 3. Then we'll divide by the sum of all the resistors making the delta again. It's 254. So we do the math here. We'll get 0.55556 ohms. Now, what have we achieved? Now, notice one thing here. I'm going to redraw the circuit from starting from this point, coming this side. So look at what we have. So I'll redraw it just without that delta. So we have this, and then we had this. So at the bottom here, remember we're trying to get the effective resistance or the total resistance. These two are in series, so this is direct forward. We can just add those two there in series. So it's the 7 and the 2, which gives us a 9 ohms in that line. So we have 9 ohms here, and then coming up to this junction here. Now for these two junctions, so at this point and at this point, this is where our delta was starting from. So if I was to just indicate that delta there, let's use a different color for that. So notice that our delta, what we had here was something that went like this, a resistor here, then came this side, and then we had something that came like this, a resistor in this line, then coming up to this point. Then we had another resistor here, coming up to the same node here. So this is what we had. Now in place of this, what we are replacing now is our star. So we have our star, which has the same effect as the delta there. So in place of this, here we have a node. So along that node, of course, we have RB. And then from here, we had another line coming towards this point. We labeled that as A. And then along this line, we had RA. Then here, of course, this is RB. And then from this point coming down, along this line, we have RC. Now, what this achieves is we now have an equivalency of the delta. So you can practically remove the delta and still have the same effect with the star, of course. So now our circuit looks like this. And of course, from here, it goes towards that terminal that goes this side. So we can rearrange this so that it looks a little bit better. So we have this line coming this side. So this is one terminal, and then this side we have our 9 ohms down here, then coming up to this node. Now our star comes this side. We have RA here, then we have RB here, then we have RC down here. So you can write it like this, or you can make it like this. So this is RA, RC, and RB this side. So notice that our circuit now looks much better. Look at where we started from. So if I was to remove this and show you where we started from something that looked like this. So we started with this. Now look at what we have. So if I was to just erase everything else, I'd like to get rid of the yellow. Okay. Getting the total resistance for something that looked like this was a little bit difficult. It was easier for us to combine these two. Of course, they are in series, and also these two were in series. But the trouble was, how do we continue from there? What are you going to do at this junction? Are you going to say that this is parallel to this? Or are you going to say that maybe this is in series with this? As in, which line are you going to take? That was the confusion with a circuit that looked like this. But look at how we've simplified it with a delta to star transformation. Now we are sure how things relate. The one down here, of course, is the 9 ohms. So we know to say the 9 ohms clearly is in series with RC, and the 2 they are parallel to RA, and then the parallel connection there is in series with RB. So this is how the delta to star transformation has made the problem much easier to work out. So from here, let's continue now to work it out the normal way, of course, since now we have made the transformation. So having made the transformation, it's clear what we have to do. We know what RA is, what RB, and what RC, what they are. So now let's find the effective resistance of our circuit. So of course, we'll start with these two. They are in series. So since they're in series, we're just going to add them. So I'm going to get the total resistance there. Let me label it with the subscript 1 there. So they're in series, we'll just add them. So this is going to be 9 ohms plus RC. Remember what RC is. So this is going to be 9 plus that 0.555 and so on. So this is going to be 9.55556 ohms. So we have that. So we can now redraw our circuit with these combined. So let's see what we now have. So we have this. Then we have our RB this side. So this is RB, this is RA, and this side, this is the 9.55556 ohms. From here, the RA and the 9.55 ohms or RT1, these two are parallel, so we can combine these two. So we can get this as R total number 2. So these, of course, are parallel. So because they're parallel, we're going to say RA. We know what RA is. We found it already. So that one is 2.2778 by 9.55556 divided by their sum. And this is going to give us 1.8394 ohms. So let's redraw our circuit. Now we have combined these two. So all we are seeing now is from here, we have that combination. We labeled it as RT2. And then from this went to connect with, in series, of course, with RB. And then this side, so from the question, if we start from the question, this was labeled as junction A, and this was labeled as junction B. So these two are now in series, so we can combine them by just adding them, so that in the end, the total resistance altogether now is just going to be the sum we had, 1.8394 plus RB. And for RB, we had 7.5926. So if we add these, we get 9.4319. Of course, we can just write this as 9.43 ohms. So this becomes the total resistance in our circuit. So this is just one example. Let's see if we can do another example to just make this more clear. For our second example, we have a question that is coming from a test paper. So this looks a little bit complicated, but not very complicated. Let's see what we have to do. They're saying for the circuit depicted in the figure, obtain the equivalent resistance RAB. So RAB, so that's literally the total resistance of everything here. Okay, effective resistance RAB, given that all resistors have a value R equal to 30 ohms. Now, how do we do that? Well, the first thing that you want to observe here is that these two resistors here are in series. We want to use the same delta to star transformation. It's going to work here, but observe that these two are in series. So before we even do anything, we can combine those two because they're literally in series. So if we were to come up with this circuit now, we have this line. Of course, everything else is just as they are. Okay, So I've redrawn the circuit. It looks a little bit scruffy, but this time I've just combined these two since they are in series. So I'm going to place them here. So those two are in series. Each one is worth 10, is worth 30 ohms. So if we get the combined resistance there for series, of course, we're just going to add them. So 30 plus 30, this is going to come out as 60 ohms. So here we have 60. The next thing that I want you to observe here is that before we even bring our star here, observe that these two resistors, these ones down here, these two are in parallel. The key thing for parallel here is that when you start from one point, you should only have two junctions. If two resistors are parallel, they should only have two junctions. There shouldn't be anything else. Picture all the other circuits here, or all the other connections. If you look at, let me say, these two resistors here, are they in parallel to each other or are they in series? First of all, you can clearly tell to say that they're not in series. But maybe, as I'm claiming here, are these two in parallel? Well, let's start. Want to see if they're in parallel, then we should only have two junctions or two nodes. So when you start from this side, you find the first node at B here. You continue, you find the second resistor, fine. But when you look at this, you found another node. And when you continue, you find another node. So these two are not in parallel to each other. One other thing that you can use to see if resistors are in parallel is that they should share these two junctions, or they should have the same common junction. So if you look at this resistor R here, so the resistor R has, or it stands at this node and at that node, which is the same 2 points where the 60 ohm resistor also stands. So they share the same two nodes, so we can argue to say that the two resistors are in parallel. Since these two are in parallel, we can combine them. So we can get their combination. Let me label it as RT1. We can just multiply the 60 by R. Each R is worth 30, so we have 30 divided by 60 plus 30. And if we do the math this side, we get 20 here. So we have 20 ohms. So having obtained this, let's redraw our circuit, but now with these combined, let's see what we're going to have. So in place of those two resistors, they were supposed to be this side. Now we're going to replace them with their combination. So I'm just going to draw it like this. So I've replaced them. Of course, they were standing at this end of this triangle and at this end of the upper delta there. So now we have reduced those, and we found this value here as 20 ohms. So everything else, this is an R, and everything else is R there. Now we have simplified everything that could work straightforward. Now the next part is to utilize the star delta transformation. So we see here that we can identify two delta transformations that can be used. So you can create the first one here. You can start from this side, coming down, then from here comes this side, and then comes this side. And then of course we can also create another one right on top, this side, and then this side, and then this side. So those are the two transformations that we're going to create here. Notice that once the two transformations have been made, the problem is going to be easier to work out. You'll see how. But one other thing I'd like you to just identify is that the two delta triangles that we are making here, the first one on top and the one down here, the two triangles are similar. They're similar in the sense that the resistors here are OR, so implying that the way we'll resolve the delta to star on top will literally be the same way we'll resolve the one down here. And apart from that, the resistor that is going to be this side will be the same value as this one will be. So the same thing here, it will be the same value. Why? Because it's the same value R, same here, same here. Even here, it's the same value, same value, same value down here. So because of that, we're going to see those similarities. With that in mind, all we need here is just to resolve one delta transformation, transform it into a star, and then we'll know exactly what the others are going to be. So let's transform one delta. So we have our delta here. Now again, it's up to you really how you want to assign the values. All I want you to get is the trick on how you find them. So we have our delta. Want this to become a star, so or a Y. So we have, let's call it a star. So we have this here and this here. So we're going to have one resistor here, another resistor here, and another resistor this side. So I want to find what this is. So I can label this as, they're just the same. So I can say this is R1, R2, R3, and then we have RA, RB, and RC. So there'll be the same value RA, RB, RC because R1, R2, R3 are all the same. So let's see. To find RA is between R1 and R2. So multiply R1 and R2, and then we'll divide them by the sum. So we divide by R1 plus R2 plus R3. So if we do this, R1 and R2 are the same. They are all R, and R is 30. So we're going to have 30 by 30 divided by R1, R2, R3, and they're all 30. So it will be 30, 30, 30, which is just 90. So this is going to be 900 on top divided by 90. So RA comes out as 10 ohms. So you can try to see if RB will be as I predicted. So of course here RB is down this side. So RB is between R1 and R3. R1 and R3 are still 10s. So are still 30s, I mean. So have 30 by 30 divided by the sum again, which is R1, R2, R3, which is still 90. Again, we see that RB comes out as 10 ohms. So with the same math, you see that RC will come out as 10 ohms as well. So here we're getting the same values for A, B, and C because those resistors are all given the value of 30 ohms. So we've seen that our star here is going to have 10 here, 10 here, and 10 there. Since this is also 30, 30, and 30, we expect that this will be 10, 10, and 10. So let's see how our circuit will now look like. So I'll eliminate everything else. I'll remove the delta and I'll remain with the transformed circuit. So I'm removing everything, leaving only the star. So look at what we have. This is how our circuit looks like. And now we know the values. This is 10. This is also 10 ohms, 10 ohms, 10 ohms, 10 ohms, and 10 ohms. From here, a few things can be observed. First and foremost, look at this. This is now in series, the same line. It's in series with the 20 ohms down here, and it is in series with the 10 ohms down here. So those three can be combined. We're going to have 10 plus 20 plus 10, and this is going to give us 40 in that line. And apart from that, observe that this line as well has a 10 ohm resistor and a 10 ohm resistor here. So these two are in series. We haven't found any junction so far. So those two are in series. So let's redraw our circuit showing only the series, only the simplified versions in each line. So in this line, we have seen to say that since these four, so the three actually, the 10, the 20, and the 30 are in series. So you can replace these by the equivalence. So see, it was 10, 20, and 10, 20, and 10. So in place of these, they were starting from here, coming up to this point. So we can substitute these by a combination. So let me take it out like this, then take it down, put our resistor here, and then bring it here. So this is 40 ohms. Okay, now that is done, the next thing that we're going to do is observe that these two, the 10 ohm resistor here and the 10 ohm resistor here, these two are also in series. So since these are in series 10, 10, so this is going to be 20 ohms. So we can remove this, and in place of those two, we're going to have 20 ohms. So we can connect it like this. So we have 20 ohms this side. So look at our circuit now. Now it looks much more workable because from here you can tell to say that the 20 and the 40 ohms are parallel to each other, and if they're parallel, we can combine them. Since the 20 and the 40 are parallel, they both stand at this point and also at that point, so you can combine those. So RT2, so in this case we're going to get 20 by 40 divided by 20 plus 40, and this, it gives us 13.33 ohms. So now we can redraw our circuit. Let's see what we get. So if we redraw our circuit, now we're going to remove these two. In place of them, we're going to put something equivalent to them. So now we only have that 13.33 ohms. Now look at this. Now we have three resistors which are in series, 10, 13, and 10. So when you combine these, so we only have the total resistance altogether, the resistance across AB, and this is going to be 10 plus 13 plus 10, and this is going to give us 33.33 ohms. And there we have it. We have worked out something that looked as complicated as this, and our answer came out as RAB is equal to 33.33 ohms. So that's how we were supposed to do it. 13 marks for all that. Now guys, in the next tutorial we're going to see some examples. We're going to see how we convert now from a Y to a delta or star to delta, and then I'm also going to do a number of examples. We'll see you guys in the